Hello everyone, welcome to LFI Debates. We are in physics class and we are continuing with this chapter 12, that is atoms. Now let us discuss about the hydrogen spectrum. And as we all know that the hydrogen spectrum is a line spectra, we say. There are two types of hydrogen spectrum that you can see, because when electron jumps from higher energy state to lower energy state, it emits radiation that we call it as emission spectra. Emission spectra you will observe like this in a white background or in a dark background. I have to make it completely dark now, it's too big. Let me take a small one. Suppose this is your dark background. In a dark background, you can just imagine as your black chart paper. Then you'll get like this bright fringes, or we call it as spectra. Like this bright patches will be formed in a dark background. This type of spectra, we call it as emission spectra, or spectrum of hydrogen. And if absorption spectra you see, then you'll see in a white background, dark patches, dark spectrums you'll see, that we call it as absorption spectrum. When an electron jumps from low energy state to higher energy state, then the spectrum observed is absorption spectra. In plural form we say spectra, singular you can say it as a spectrum. So these are the two types of spectrums that you can see in hydrogen atom. Now the spectrums that were observed in ultraviolet region, you have the Lyman series, then Balmer series. Balmer was the first person to observe spectral lines for hydrogen atom in the visible region. And then you have the other three, that is Pfund, Brackett and Paschen series, or serially if I say Paschen, Brackett and Pfund series. These series are observed in infrared region of the spectrum. Let us draw and see now. The spectral lines, if you draw, this is the ground state, n equal to 1. And the energy in electron volt, we know that in the ground state the energy is minus 13.6 electron volt. So if we draw the states like this, n equal to 1 the ground state, then n equal to 2, then n equal to 3, n equal to 4, n equal to 5, n equal to 6, n equal to 7, and so on. Here the energies, what you have to do, your formula was minus 13.6 divided by n square. This is the nth term. E1 it is minus 13.6. E2 13.6 divided by 2 square is 4. 4 4s are 16. 4 3s are 12. 4 4s are 16. Minus 3.4. This is minus 3.4 electron volt. the energy in electron volt. This represents y-axis. Like that, third one, minus 13.6 divided by n will be 3. 3 square is 9. 9 ones are 9. 4, 6, 9 5s are 45. And 9 ones are 9. Minus 1.5. Minus 1.5 electron volt. Then E4. E4 will be 0.4 square is 16. So it will be around divided by 16. 16 8 times 48, 128, 8 times 128, 80, then 16 5 times 0.85 is minus 0.85 electron volts. Then E5 25, so 13.6 divided by 25, 5 times is 125. This decimal is there. 4 times minus 0.54, then E5 this is minus 0.54, E6 6 square 36, 13.6 divided by 36, 144, around 0.3, 3, 6, 18, 8, 1 in hand, 9, 10, 8, 2, 0. Then around 9 will come, I think. 9, 6 are 54, 5 in hand, 9, 3, 7, 7, 22, around 32. Now this is bigger. 8, let us see. 8, 6 are 48. 8, 3 is 24, 28. This is also slightly more, that means it is 7. 0. Minus 0.37. Like that you can, this is for this value, this one is for this one is for this, this one is for this. Like this you can do. The first series is your Lyman series. In Lyman series, if an electron jumps from 2 n equal to 2, 3, 4, 5 and so on to n equal to 1 in the first step, if it jumps, then the series observed is called Lyman series. Then the series observed is called Lyman series, and in such series the wave number 1 by lambda will be the Rydberg's constant are 1 by n1, that is 1 square minus 1 by n2. Your formula is 1 by n1 square minus 1 by n2 square. N can take values, n2 can take values 2, 3, 4, 5 and so on. With 2, 3, 4, 5 and so on. This series we call it as Lyman series. You can draw and show like this: from n2 if it jumps to n1, from n3 if it jumps to n1, from n4 if it jumps to n1, n5 if it jumps to n1. So from any higher series other than 1, if it jumps to n1, then that series we call it as, this line will go up to 0. Ultimately it will go up to, this is a series limit, we can say series limit. Like that, if you go on drawing the line, then it will become 0. Energy will become more and more and reach towards 0. And ionized atoms you can find that side. Then n equals 7 to n equal to 1, then the series we call it as Lyman series. and you can observe this in which region of the spectrum, then we'll say UV region, ultraviolet region. And the second series is your bracket series, that is visible in visible region. For bracket series, the second one, the second series is your Balmer series. In Balmer series, the electrons, they jump at n equal to 2. From n equal to 3 they can jump, from n equal to 4 they can jump, from 5 they can jump to n to 6, 7. If they jump to n2, then that series we call it as Balmer series. And this series is visible in visible region. In this case, the wave number 1 by lambda is equal to r. 1 by n1 will be, it will jump at, it will not come to n1. Here n1, the first value will be here 2. So it will be 2 square minus 1 by n2 square. Here n2 indicates jumping from n equal to 3, 4, 5 and so on, where n2 is equal to 3, 4, 5 and so on. So this is the expression for the wave number in case of Balmer series. Then comes your Paschen series. In Paschen series, the wave number you will give like this, r 1 by 3 square. The electron will jump at n equal to 3 from any of the higher orbit. Then we'll get Paschen series. In Paschen series, it is visible in infrared region. Paschen, bracket and P-fan, they are visible in infrared region of the spectrum. Infrared region of the spectrum you can see. And their formula for wave number will go like this: 1 by n2 square. Here n2 will take values 4, 5, 6 and so on, jumping from n equal to 4 to n equal to 3, n equal to 5 to n equal to 3, like that. You get the series as Paschen series. Then the fourth one, that is your bracket series. The wave number 1 by lambda is equal to r. 1 by 4 square should jump at n equal to 4 minus 1 by n2 square. Here n2 will take values 5, 6 and so on. That series we call it as bracket series. It should be it should jump at n4, should come like this. This is your bracket series. This is also visible in infrared region of the spectrum. Then the last one, that is your P-fan series. This is also visible in infrared region of the spectrum. 1 by lambda square minus 1 by n2 square, where n2 will take values 6, 7 and so on. So it should jump at n equal to 5. And 5 is here, so you will get here your P-fan series. These are the 5 series of hydrogen atom observed till now. So this is your hydrogen spectrum. 5 line spectrums are observed in hydrogen spectrum. Now let us see a very important topic, which has been asked previously in board exams. That is de Broglie's comment on Bohr's quantization condition. That angular momentum is an integral multiple of h by 2 pi. That is your Bohr's quantization condition. What de Broglie has said, let us see. According to de Broglie's according to de Broglie, a stationary orbit is that a stationary orbit is that which contains or which has an integral value of de Broglie standing waves associated with an electron. This is what he said. So a stationary orbit, one round to go, the total distance traveled, or in other words we can say the distance traveled by an electron that is equal to the circumference of the orbit, that we take it as 2 pi r. If radius of the nth orbit if we take, then we can write 2 pi r, and that is an integral multiple of de Broglie's standing waves, where n takes the value 1, 2, 3 and so on, principal quantum number. Now if we write it like this, it's equation number 1. De Broglie's wavelength lambda is equal to Planck's constant divided by momentum p. So like this we have come across. Then lambda is equal to h divided by momentum is mass into velocity. Let us take this as equation number 2. This is your de Broglie's hypothesis, from where we got lambda is equal to Planck's constant divided by momentum. If you put the value of this de Broglie's wavelength here in equation 1, putting the value of lambda from equation 2 in equation 1, we get here 2 pi Rn is equal to n lambda, n, and this is lambda, n, and your lambda is h by mv. V also you can put it as the velocity in the nth orbit, because velocity of electrons in different orbits is different. So you'll get from here mvr, mv, if you multiply this, mvn rn, that is your angular momentum, is equal to nh divided by this 2 pi, you can bring here 2 pi. and this is the expression for angular momentum, and this is your quantization condition of Bohr, that you can get it from de Broglie's comment. It both matches. You can see here angular momentum is conserved. It is an integral multiple of h by 2 pi. So this is your de Broglie's comment on Bohr's quantization condition. It exactly comes out to be the same. Let us see the limitations of Bohr's model of the atom. There are some limitations. First of all, it is applicable to simple atoms with Z equal to 1, is like hydrogen and hydrogen-like atoms, whereas in other atoms when Z value changes 2, 3, 4, then this theory fails. The second limitation is that it is only, if you put it much better, applicable to simple atoms. It fails to explain the fine spectra of hydrogen atoms. It explains line spectra, it explains the different spectrums produced by hydrogen atom, but while there are some fine spectra that are observed, still some more fine spectra are observed in hydrogen atom. Those things Bohr's model could not explain. And then the third one, Bohr said that the electron revolves in a circular orbit, the orbit is circular, but now we know that there are some orbits which are elliptical, which are not circular, but it can be even elliptical like this. So this part also Bohr failed to explain. It failed to explain why elliptical orbits are present in an atom. So this elliptical orbits, this part he could not explain. He only explained about the circular orbits. Some are circular, some are elliptical, but this elliptical part he could not explain. So he fails, this theory fails there. But for you, the Bohr's model is the most important part for your exam. Now we'll be doing some numericals as well. You cannot leave anything from here. It's for exam. You have to get ready. You have to get prepared. But later on in higher classes, you'll study about the quantum mechanical model of the atom. So to know the quantum mechanical model of the atom, this theory is very, very useful. So you need to know, because inside the box, if you don't know, then outside the box to think, it becomes impossible. So in inner things you have to know, and slowly the outside ones will start learning the exact things. Let us do some numericals and see now. Here, Bohr's theory of hydrogen atom, it looks like very difficult to remember. The formulas are very complicated, but it is not so. When we solve the numerical, then you will come to know that what are the relations and what things I have said while deriving the relation. There you will focus it nicely. You will get it in a very easy way. Just see the solution that you will be doing, and it's very important. You cannot leave any numerical here. You must know the radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 to the power minus 11 meter. It is given to you. The innermost electron, this is your nucleus. The innermost means the first orbit at n equal to 1. The energy is given as 5.3 into 10 to the power minus 11 meter. Now you are asked to calculate its radius in n equal to 2. N equal to 2 will be here, suppose n equal to 2. Then already we discussed that the radius are in the ratio 1 is to 4 is to 9 is to 16 is to and so on. That you have to know. At n equal to 1, if it is this one, this is the value given to you. At n equal to 2, it will be how many times? That at n equal to 1, it will be 4 times. 4 times this and this radius. 4 times this radius. Then you will get the radius in n equal to 2 orbit. Is it okay? Let me write down now. General formula you can make it like this also. For the first one, Rn, suppose radius in the nth orbit is equal to n square times r1. Like this you can make the formula, n square times. Square 1 is 1, 1 square is 1, 2 square is 4. So here if you put n equal to 2, when n is equal to 2, Rn, R2, it will become 2 square, n equal to 2, and R1 or R, it is given to you already, 5.3 into 10 to the power minus 11 meter. Now if you multiply 4 into 5.3, 4 3s are 12, 2 1 in hand, 4 5s are 20, plus 1 is 21, decimal is after 1 digit, into 10 to the power minus 11 meter. Scientific way, if you write this decimal, you bring this side, 2.12 into 10 to the power minus 10 meter. So this that easy it is, you can solve it very nicely. Now let us see the second one. In the second case, here also you will have to focus on the energy. Energy, total energy that we got it, the total energy was equal to sum of kinetic energy plus potential energy. This gave us the total energy. Kinetic energy plus potential energy, if you add, you get energy. But this total energy and kinetic energy differ by one sign only. If kinetic energy is positive, potential energy is if total energy is positive, kinetic energy is negative. They differ only by sign. The rest, all the values are the same. So if you look here, the total energy of an electron in second excited state. Here this second or first or third, we are not interested. Everything is given in the second excited state of hydrogen atom. The total energy is given as, we'll write it as E, the total energy E. It is equal to minus 1.51 electron volt. Now you have to find out the kinetic energy. Now kinetic energy differs from total energy by sign only. The negative of kinetic energy is total energy. So kinetic energy if I write as K, it will be negative of the total energy. So negative of negative will be positive 1.51 electron volt. Like this you can find out the kinetic energy. Now if you look here, to find the potential energy in the same state, potential energy will be total energy minus kinetic energy. So potential energy U is equal to total energy minus kinetic energy. So total energy is minus 1.51 electron volt, minus kinetic energy is 1.51 electron volt. So minus into minus minus, we have to add it. Add it, 1 plus 1 is 2, 5 plus 5 is 10, 0, 1 in hand, 1 plus 1 is 3. So it will come out to be minus 3.02 electron volts. On other words, we can say that potential energy is 2 times of kinetic energy. If you can remember this, directly 2 times the total energy, if you multiply also, you will get the potential energy. Like this, numericals are related with the concepts. It is not related with the derivation, remember here in Bohr's theory of hydrogen atom. With this, I will come to the end of this chapter. Hope you all cooperate and keep on practicing, keep on studying. God bless you all. Thank you.